wearing your wonderful and wearing your UC Irvine accoutrement. We appreciate the representation. Welcome
As
everyone.
always.
My name is Dr. Joni Rixodi, and I direct 2 units of statisticians on campus. If you haven't joined us before, one is in the statistics department, which is the UCI Center for Stat Consulting. The other is a unit called the BIRD unit, which is the Biostatistics, Epidemiology, and Research Design unit over in the Institute for Clinical and Translational Sciences. So we're a group of epidemiologists and statisticians that help with data analysis, statistical support, statistical analysis planning, grant support, all the fun things that make your research project successful, ideally. And one of the works that and one of the initiatives we do is we like to train you to the extent you are interested on a variety of type of statistical software and methodologies. And so we are blessed to be joined by Dr. Chuck Huber, who works for Stata Corp, who graciously over the years has done these free Stata seminars and webinars for us on a variety of topics in Stata and how to do different types of analyses. So today we're going to be doing intro to structural equation modeling. I'm a SEM fan, so I'm excited for you all to learn about it. Chuck has worked for Stata for a number of years, does these talks all over the country, has been a faculty member before, comes with a wealth of experience on a variety of applications. So do not hesitate to ask him questions as we go along. I know he likes those, so feel free to unmute yourself. Margaret and I will be managing and moderating the chat. So if you have questions and you want to pop them in the chat as well, feel free. And today again is for you, so feel free to engage. I always ask people if you are willing and able to turn on your camera so Chuck can see your bright smiley face, so he doesn't have to talk to black boxes. And with that being said, I'm going to turn it over to Chuck.
Okay, thanks, Joni, and thanks for setting this up. And Margaret, thanks for all you do to set this up, and glad to be here again. So I'm going to shut off my camera and save a little bandwidth here and share my slides. Oh, sharing is not turned on. I think I have to be co-host.
I think she just, it looks like Margaret just put a thumbs up. I think she just made.
Okay, there we go. All set. Perfect. Thank you. Okay. Can everyone see the slides okay? I'll take the silence as a yes. Okay. And as Joni said, if you have questions along the way, please feel free to jump in and just unmute your microphones and ask away. Today we're going to be talking about, as Joni said, structural equation modeling. I'm going to assume you know nothing about structural equation modeling. We're going to start at the very, very beginning. So if you're not familiar with this topic, don't worry about it. We're going to start simple. You can download all of the materials, the slides, the data sets, and the do files, and the path diagrams, which we'll learn about shortly. You can grab those all here at tinyurl.com/2021sim. I guess it's been 4 years now since I overhauled this talk. This was a pretty old talk, and it was too long, and so I've tightened it up some. So it should be down to about an hour now without questions. And we have a little extra time today if we want to do questions. But again, feel free to ask questions along the way. I also pasted this link into the comments box. So if you want to grab it there, all you need to do is click on the link and it'll take you right to the website. Okay, so what are we going to talk about? So we're going to start with just what is structural equation modeling and do sort of a basic non-technical introduction. And then we're going to have to talk about jargon and assumptions. There's a lot of jargon to do with SIM. People call this SIM for short, SEM, for structural equation modeling. There's a lot of jargon and some new concepts. And I think that's one of the hurdles that prevents people from using these techniques or these tools, which is unfortunate because these are really powerful and they're not as unfamiliar as you may think they are and as they may sound. And so I'm hoping by the end of this, we'll make sense of it and you'll feel more confident using these models because they're available in Stata. If you have Stata, they're available and they're easy to use. It's just getting over the hurdle of some of the jargon and concepts. So then we're going to talk about how to do structural equation modeling in Stata. Then we'll work some examples and I'll give you some other resources and we'll wrap up. Okay. So what is structural equation models? Well, structural equation modeling. There are lots of technical explanations, but I like to think of it as basically three things. First, you can explore and test relationships among variables. And notice I said among because rather than talking about this group of predictors predicts an outcome variable, This allows us to explore and test the relationships among variables, which leads us to point two. These models can include a system of equations. So you can think of them as a system of regression models rather than just a regression model. And this will make more sense as we go along. Now, because of this, a lot of other things that you're familiar with are actually special cases of structural equation models. So, correlation is a special case of a structural equation model. Linear regression, or factor analysis, or multivariate regression. These are all special cases of structural equation modeling. And as we'll see later on, you can fit all of those kinds of models as structural equation models. And so I think this is a lot more familiar than you think it is. Uh, but hopefully we'll see that by the end. All right, some jargon and assumptions. So let's start off with the jargon. Path diagrams, observed and latent variables, paths and covariance, endogenous and exogenous variables. What does all this stuff mean? What are these things? So let's start off with path diagrams. This is one of the things that sort of distinguishes structural equation modeling is the path diagram. So it's a way of drawing the model that we'd like to fit. And I'm going to explain all the parts of the model here shortly, but this is one of the hallmarks of a structural equation models, these path diagrams. You can actually draw the model. And I think it's very helpful for visualizing what we're interested in. What are the interrelationships among these variables? So let's talk about the parts of a path diagram first. So there are two kinds of variables that you'll see in a path diagram or a structural equation model. They are observed variables and latent variables. So observed variables, I've drawn those in the path diagram with things with corners or rectangles. Sometimes you'll see them as squares, but they have corners on them. So that differentiates the way observed variables are presented in the path diagram. So they're in blue here. Observed variables are exactly as you would imagine. They're things that we observe and we measure them, and they are in our data set. So that's what we normally think of as a variable in a model. So that's going to be familiar. The unfamiliar part are going to be these ovals drawn in orange here, and those are called latent variables. Latent variables are unobserved variables that we wish we actually had observed, but we can't for whatever reason. Either we didn't or we can't. They're often thought of as being the underlying cause of the observed variables. So, for example, down the left-hand column here, I have these observed variables called depress Q1, depress Q2 through depress Q5. Those could be the responses to depression questions, to questions on a depression questionnaire. And so that's what we observe are these first five the responses to these first five depression questions. But those are often thought to be manifestations of emotional depression. So the thing we're really interested in is emotional depression, which is the latent variable here drawn in with an orange oval. So we're interested in emotional depression, but and we don't observe it directly, but we observe it indirectly through the observed variables or the manifestations or manifest variables, depression questions 1 through 5. Now, we may also be interested in physical depression symptoms. And so I've drawn that here with an orange oval on the right. And that may manifest itself as the responses to depression questions 6 through 10. So we observe the depression questions, but they're thought to be manifestations of these latent variables, which we don't observe directly. And we're going to learn about those and estimate the latent variables mathematically, and we'll talk more about that later on. So again, if you look in your data set, you're not going to find emotional and physical in your data set. Those are parts of the model that we're going to estimate. Okay. Next up, so those are the blocks, the squares and the ovals. Now, next up are the things that connect those with each other. So there are two types of connections, paths and covariance. So the paths, I've drawn those with blue lines. The paths are like regression coefficients. So notice that the paths have a one-way arrow. They go away from the latent variable towards the observed variables. And the reason for that is we, again, believe that the latent variable manifests itself or causes the observed variable. So we would believe that emotional depression manifests itself in the response to depression question 1 and the response to depression question 2 and so forth. Okay. So we again interpret those as just like you would a regression coefficient. A unit change in emotional depression leads to a whatever that path coefficient is, change in the depression score that we observe. Okay. So those are the paths, the one-sided arrows or the directional arrows. The other kind of connection we can have is a covariance. And notice that's drawn in orange here, and it has an arrowhead on both ends. So covariance or correlation means that two things can covary, but one doesn't necessarily cause the other or influence. They're just associated with each other in some fashion, or they tend to covary. So you can have correlation among the errors for observed variables or with the latent variables in your models. Okay, so two kinds of connections, paths and covariance. Next up is endogenous and exogenous variables. So these are labels for variables. And this counts for both latent variables and observed variables. I'm only using observed variables here. What happens is in normal regression modeling, we typically think of a dependent variable and independent variables, or an outcome variable and predictor variables. This group of variables predicts the outcome. But with a structural equation model, there are arrows pointing all over the place in the model. And so if we think about drug score, if we look at drug score in the top right here, drug score, there's an arrow pointing from drug score towards math score. So in this case, we might say that drug score is a predictor of math score. So math score is the dependent variable, drug score is the independent variable. But the problem with that jargon in this context is that drug score is also the outcome for depth score. So we have a variable in the bottom right called depth score, or depression score, which we think predicts drug score. Well, so what is drug score then? How do we label it? Is drug score a dependent variable or is it an independent variable? In one context or one part of the model, it's an independent variable, and another part, it's a dependent variable. So that terminology breaks down in the context of structural equation models. So we're going to use some different jargon. Any variable that serves the role of a dependent variable is called an endogenous variable. So if it's an outcome in any part of the model, or more specifically, if there's an arrow pointed towards that variable, it's considered an endogenous variable, and I've colored those with orange lines here. So math score is an endogenous variable because it has arrows pointed towards it. Drug score is an endogenous variable because it has arrows pointed towards it as well. And then we also have the exogenous variables. Exogenous variables serve the role of independent variables. They don't have any arrows pointed towards them, okay? And so they serve the role or we're going to call them exogenous variables, okay? I forgot to mention these round things hanging off of here. So any endogenous variables, because it serves the role of a dependent variable, any endogenous variables are going to have these error terms hanging off of them. That's what these epsilon 1 and epsilon 2 are. So those are the error terms like in a regression model. So we can think of those like that. Okay, they're thus the epsilon. All right, so that's some of the jargon that we're going to be using, and it's a little confusing at first, but once you get the hang of it, it makes sense. Okay, what about the assumptions we're going to make when we fit these models? Well, first is large sample size.
Hey Chuck,
Yes, question?
yes. Real quick, is there a sort of functional difference between the double arrow and the single arrow? Like you mentioned before, there's like the path relationship, so like regression coefficients, and then the double arrows covariance.
Yes.
But if I think about, I don't know, like a regression coefficient, like what's the relationship between two variables? As one goes up, I expect the other one to go up or go down, and then similarly
Right.
covariance. Is there sort of like functional difference between them in terms of the modeling or the
There is. That's a good question. In the sense that it's directional in the sense that we think the emotional depression causes or influences the response to depression question one. So there's a directionality to it. One influences the other. So in this case, we would think of emotional as an exogenous or independent variable influencing the dependent variable or endogenous variable depression question one. So there's a directionality to it, and that's what that path coefficient quantifies. But the covariance, because it's a double-headed arrow, that's just saying that the two covary or are they correlated. So if we standardize it to a correlation, that correlation is bounded between -1 and 1, right? Whereas a regression coefficient or a path coefficient could be any number, depending on the magnitude of the things you measured. So there really isn't a boundary or a constraint per se, a natural constraint on those path coefficients. Whereas on a correlation, the covariance curve, if it's a correlation, it's bounded between -1 and 1. If it's a covariance, it can be different. But we're not saying that one causes the other with that covariance curve or one influences the other. We're just saying that they covary. One tends to go higher, tends to go with higher, or lower tends to go with higher, or vice versa. Um, does that answer your question?
That does. That helps a lot. Thank you, Chuck.
Okay, sure. Yeah. Any other questions while we're paused? Okay. So back to model assumptions. So large sample size. In general, we want larger sample sizes for these more complex models. Now, the obvious question comes up, well, how large is large? And nobody ever wants to say. And I'm not really going to say here because I don't want to be quoted as saying, well, you must have at least 10 observations per whatever. If you kind of browse the books and the literature, you'll find numbers ranging from about 5 to 20 observations per free parameter. So that's per free parameter, and we'll talk more about that later on, but it's not per variable in the model, it's per free parameter, and you can have multiple parameters in the model. So it's not just it's not necessarily 5 to 20 per observation or per variable. But again, larger is better. These are not the kinds of models you want to be fitting with 20 or 30 observations because you may have 10 or 15 variables in the model. And then if you're estimating that with 30 observations, that just doesn't feel right. And mathematically, it doesn't make a lot of sense. So larger, when in doubt, larger sample size is better. Okay. Now, for regular sim, and we'll talk about differences later between regular structural equation modeling and generalized structural equation modeling. But for regular structural equation modeling, we're assuming multivariate normality of at least the endogenous variables. And the reason we make this assumption is because we're going to use maximum likelihood to estimate the parameters. And when the likelihood function that we're going to maximize is a multivariate normal likelihood function. So that's where this assumption comes from. So we're assuming multivariate normality of at least the endogenous variables in the model. The other thing that we're assuming, and this is true of any regression model, we often don't think about it, but it's particularly important with structural equation models, is correct model specification. So what we mean by that are all of the necessary paths and covariances specified? Did you leave anything out? Any connections between the variables? Second is, are there any omitted variables? So if you've ever talked about endogeneity, issues with endogeneity and omitted variable bias, have we left out any variables that are important? Another thing we might need to think about are the relationships between these. Are they necessarily linear, or do we need a quadratic term or a cubic term in the model? And also, do we need any interactions between these variables? So that's what we're referring to by correct model specification. You never really know for sure whether it's correctly specified, but it's something you need to stop and think about. And a lot of times, if your model will not converge, one of the issues could be an incorrect model specification. And that's why we're not going to do it so much today, but when you fit these kinds of models, I think it's very, very important to do graphs, to do some basic plots, scatter plots and things like that, to look at the relationships between the variables, because sometimes you may have a curvilinear relationship, like an A shape or a U shaped relationship between two continuous variables. And you may be trying to fit the model as having a linear relationship between two variables when in fact it's quadratic or cubic or something. So the best way to identify those issues are to look at graphs, scatter plots, and basic descriptive plots before you start fitting these complex models. Okay. So any questions about the jargon and the assumptions? Okay.
I have a quick question.
Okay, sure. Yeah, go ahead.
So what exactly goes wrong if you misspecify your model? Is it just that the structural equation model won't converge, or does it have like the best linear approximation to the true model, or what's going on if you have the incorrect model specification?
Yes, that's another excellent question. So if the model isn't specified correctly, the first issue you could have, let's start at the most sort of basic, I suppose, is if you specify a model that's so disconnected from the data that does not model the data correctly as the data is, the model may not converge. The software won't converge. And I have friends who occasionally will send me an email say, "Oh, the model, there's something wrong with your software. The model won't converge." But then if you back out and start doing some basic descriptive plots, you'll notice that they're trying to use they're specifying relationships in the model that don't reflect what the relationships in the data. So, one of the classic examples of this is the relationship between anxiety and test performance. That has a very distinct hump-shaped relationship. If you do a scatter plot, you can see very clearly there's a hump shape to it. If you're too chill, you don't perform well on test. A little bit of anxiety is kind of good. It kind of gets the juices flowing. But if you get too nervous taking a test, then you kind of freak out and you do poorly on a test. So there's kind of a peak performance if you look at a scatter plot of anxiety, like test anxiety and test performance. It has a hump-shaped relationship. And so if you try and build a model that has a linear relationship, it may fit so poorly. The model that you've specified may fit the data so poorly that the model cannot converge. And so that could be the first problem, is that the model just doesn't converge at all. Then the second problem could be, which in some ways is worse, is that the model converges, but it doesn't really accurately reflect the data. I often use the analogy of painting. If I were to say, I'd like for you to paint a portrait of my son, but you've never seen my son, or you've never really taken the time to look at a photo carefully, or you just glanced at it quickly, it would be difficult to paint a portrait of my son. Same idea with data. If you don't stop and take a look at the raw data and the relationships between the variables, you may build a model that's not an accurate representation of the data. And that's why I'm a big proponent of doing graphs. And I've unfortunately taken a lot of that out of this talk. That's how I got it, partly how I got it down to an hour. Um, but I do think it's important to look at basic graphs, look at scatter plots, look at box plots of the relationships among the variables to make sure that you're specifying these things correctly. Should the relationships be linear or quadratic or cubic? Do you need interactions? Often it can be obvious from scatter plots that you need an interaction term in there. The relationship between two variables may be very dependent on some third variable. I mean, imagine two scatter plots for two different groups. The relationship may be sort of upward trending for one group and downward trending for another group. Can't think of a good example off the top of my head, but interactions may be important, and a good way to identify that is again by looking at descriptive plots. So I would say that the second situation is worse. Your model converges, the software gives you parameter estimates, but they don't accurately reflect the patterns in the data. So, yeah, those are problems that you can have with model specification.
I
And you never really know. You never know for sure because, again, all you really have is a sample from a population. And ultimately, we're interested in the relationship among these variables in the population. So, even if even if you fit the model well to the sample, if your sample doesn't accurately represent the population, then that can cause issues as well. I kind of feel like I'm rambling or pontificating now, but does
No,
that
those
sort of
are
answer your question?
yeah, it does. Those are all excellent points. And then thinking about like some of the path diagrams you showed earlier, some of
Mhm.
those are kind of complex models with like multiple arrows pointing at like a single variable. Are there sort of like plots or diagnostics for those types of relationships? I can't even think about like how to visualize, I don't know, if I correctly specify drug use in this path diagram or something like that.
Right. So that's one of the things we'll talk about along the way later on, but that's an excellent question. Two issues. One is I would not fit this all at once. And I'll show you some strategies towards the end, but um you probably don't want to draw this model, put it in the software and ask it to fit it, excuse me, all at once. I would do this in pieces. And again, we're kind of getting ahead of ourselves, but I would look at this emotional depression part all by itself first, because that's kind of its own thing. In fact, early on, you would think of it as an exploratory factor analysis type question. Do these 5 questions, are they really correlated with each other? Are they really all getting at emotional depression? And do they hang together as a latent variable well? So that's kind of a theoretical question and a statistical question. So I'd probably fit that. Some people call it a measurement model by itself, just the emotional part. Same thing with the physical depression stuff. I would probably fit that as its own separate model and explore it very carefully on its own. Same thing with the drug use questions. And we're going to do that as we go along through here. And then once we're confident that those latent variables are measuring what we think they're measuring, then we can start talking about, well, okay, does that emotional depression, does that influence math score? And does physical depression influence math score? Does drug use overall influence math score? And then we may want to take into account, whether the student is male or not. What's the student's age? I even have a multi-level latent variable in here because if the data were nested within classroom, you might want to allow for the possibility of clustering, kids in classrooms, that sort of thing. But that's one of the nice things about these models is that you can build these very rich models. But you're right, they're very complex, and you need to sort of think through them very carefully and build. I suggest building them up slowly, uh, the pieces of them individually. The other part to that question is fit statistics. How do you know if this model fits the data well? And there are a whole blizzard of fit statistics. It's kind of its own little cottage industry of fit statistics. And I removed all of those equations. Again, this used to be about 130 slides, and I think I have it down to about 65 now. But one of the things I did was remove all the equations for all those fit statistics. But there are a bunch of them, and they not often, but sometimes disagree. One statistic will say, yes, this model fits the data well, while another fit statistic may say, no, it doesn't fit that well. So, yeah, but your point is well taken. These are quite sophisticated models, and that requires a lot of care and thinking about it when you're building them and assessing them.
Chuck, I was also going to chime in and just say too, the reason why I tend to take the approach you take around assessing the different measurement models separately is that I found that if the measurement models, the latent variable fits are poor, once you start adding other complexities to it, those fit statistics typically don't improve. They either
You're right.
or they depreciate significantly. So
Yes.
you really do owe yourself, because otherwise you'll fit this big model and say it doesn't, it like the fit statistics are poor, but then you don't know what aspects of it are driving that unless you've
Right.
and to do that work individually for each of your latent variables.
Oh, absolutely. It's not going to get better. It's only going to get worse. I totally agree. And ideally, I've put these latent variables in here. Ideally, you're using a known questionnaire like the Beck Depression Inventory or something like that, where you didn't just make this up out of thin air. Chances are you have purchased a license for using the Beck Depression Inventory or one of the many depression inventories, and they have well established psychometric properties. And so, but we're just modeling them correctly here. Anyway, did we answer your question?
You did. So take it in pieces. And
Yes,
all right.
absolutely.
Thank you.
Sure. Thanks for the questions. Okay, where are we? Okay, structural equation modeling in Stata. How are we going to actually do this? So there are actually 2 structural equation modeling commands in Stata, and they're similar, but they're quite different in some important ways. So the 2 commands are sim, SEM, and the other is GSEM, GSEM. The sim command fits traditional structural equation models. In that sense, what I mean by traditional is we're going to have continuous endogenous variables. So those endogenous variables must be treated as continuous, and we can have continuous observation level latent variables. Okay. So that's traditional structural equation modeling. So normally if you pick up a book on structural equation modeling, that's what they're talking about, is what the sim command does. Now, there's a more sophisticated version of sim called generalized structural equation modeling. And a way you might think about this is linear models, linear regression, versus generalized linear models. It's the same idea with sim. So generalized structural equation modeling means that we can have generalized endogenous variables. And we'll talk more about that in a moment, but essentially that means we can have endogenous variables that are binary, are ordinal, are multinomial. You can even have survival endogenous variables in these models. So that's one of the things we mean by generalized, that the endogenous variables don't have to be continuous anymore. The other thing is that we do still include continuous observation level latent variables, just like SIM, but now with GSIM, you can include multi-level latent variables. So you can fit multi-level structural equation models. You can do that with SIM, but not, well, you can do that with GSIM, but not with SIM. The other thing you can do with GSIM is you can have categorical latent variables, which are also often called latent class analysis. And next month, we're going to talk all about latent class analysis, LCA. But essentially, that's a generalized structural equation model that uses categorical latent variables rather than continuous latent variables. So you can do that with GSIM, but not with SIM. So GSIM is much more flexible and powerful, but there are some things there's some limitations that brings with it. So you would think, well, why don't we just use GSIM all the time? There might be times when SIM is actually better, and we'll get to touch on that a little bit along the way here. So the syntax, we talked about path diagrams. I want to sort of compare and contrast the path diagrams and the syntax for SIM. So this is the syntax at the top for a SIM command for the path diagram at the bottom. Now, this is where things can become a little bit confusing. So this is the path diagram at the bottom. So I have four observed variables, 3 exogenous, 1 endogenous. So x1, x2, x3 are the exogenous variables, and they are all thought to be predictors of y. So you can kind of think of this like a regression model. Now, that's a fairly simple path diagram, and at the top we have 4 different ways we could use the syntax to write that model. The top one is probably the simplest, and it's probably how I would write it. So you can type sim and then in parentheses put y, and then we're going to have that little fake arrow. So it's a less than and a dash next to each other. It looks kind of like an arrow. And then x1, x2, x3. So what this is suggesting is it's a bit like a regression model. x1, x2, and x3 are predictors of, there's an arrow pointing at y. Okay. So that's one way you could write the syntax. But Stata doesn't care about the order as long as the arrow is pointed in the correct direction. So the second row here where it says sim, I can have x1, x2, x3, and then a right arrow pointed towards y. That's exactly the same syntax. You'll get exactly the same results, just a different way of specifying the model with the syntax. Stata doesn't care. Now, another way you could do this is to bundle each of the paths in their own set of parentheses. So the third row here, it says sim, and I have x1 predicts y, and in a second set of parentheses, x2 predicts y, and another set of parentheses, x3 predicts y. So that works as well, and you get the exact same results. And then the bottom row, I'm not going to read it to you, but it's basically the reverse of that. The directionality of the x's and the y's is reversed. All 4 of those syntaxes will work, and all 4 of those syntaxes, is that a word? All 4 of those versions of the syntax will work, and they will give you the exact same output, same parameter estimates. So the syntax makes no difference in your result. It's just a matter of personal taste. Now, when you use the Stata's structural equation modeling builder, and I'll show you that here shortly, when you use the builder, it's going to spit out the syntax, I believe, in the bottom version. Maybe line 3, but I think it's line 4 actually. It's going to generate the syntax for you, and it's going to look really messy like this one, the 4th line here. And what you can do if you get that and you don't like that, you can combine that. You can combine those parentheses into one. So anyway, that's the sim syntax for a fairly simple path diagram. And again, there's a builder I'll show you in a moment that will generate the syntax for you. You can draw the model and then it will generate the syntax. So here's another sim syntax example that includes a latent variable. So let's say that we had a fairly simple measurement model. So I have 3 observed variables, x1, x2, and x3, and I have 1 latent variable, L1. So the top, and I believe L1 is manifests itself in the responses to x1, x2, and x3. And notice I have these little error terms hanging off of each one as well, because these are all like little regression models in here. So there are 3 variations, really 4 variations on the syntax. You could do the 4th line and reverse the 3rd line in the other direction. But anyway, I could type sim L1 predicts x1, x2, x3. So notice the arrow points away from the latent variable towards the observed variables. Also notice that the L for the latent variable is capitalized. So Stata is expecting latent variables to begin with a capital letter. And if you do that, what's going to happen is Stata is going to check the data set. If it finds the variable L1 and it's not in the data set and the L is capitalized, Stata will assume that that is a latent variable. Now, to be explicit about it, you can type comma latent L1 at the end, and that will tell Stata explicitly, hey, L1 is a latent variable. Now, there is a slight issue with this that you need to be very careful, because this bit me once and I hadn't really thought about it. If you have a variable, an observed variable in your data set, and you accidentally type that observed variable with a capital letter, so let's say you had age in your data set. So age is all lowercase, but you accidentally type it with a capital A. If you type age with a capital A, and that's a typo, Stata won't give you an error. With SIM, what it's going to do is it's going to assume that age is a latent variable and treat it as such. So you have to be really careful with capitalization when you're fitting structural equation models, because a typo where you like that can lead to Stata thinking that something with a capital letter is a latent variable when it's not. It's just a typo. Anyway, so if you're going to be using latent variables, begin them with a capital letter and or include this latent option at the end so that Stata knows that that is a latent variable. Now, just like with the other sim syntax, you can reverse the direction. So we could have x1, x2, x3, and then the left arrow from L1. Or we could split these all out into separate sets of separate parentheses. And you could reverse the direction. I don't know why I didn't put that in there, but you could. Okay. Now, GSIM is similar. The basic setup of the GSIM syntax is the same, but there's something we're going to have to add to it, which is the family and the link. So with GSIM, here I've set up a path diagram for what's basically a logistic regression model. I have predictors or exogenous variables x1, x2, and x3, and I believe those are predictors of y, which is the binary endogenous variable. So y is binary. Because it's binary, I want to use the Bernoulli family, distribution family, and the logit link function. So if you're familiar with the generalized linear modeling jargon, that's exactly what this is. It's just like generalized linear models. Bernoulli family, distribution family, and the logit link function. Now, because that's such a popular combination, we actually created a nickname for that, or what's the word for that? I'm blanking. Anyway, it's a nickname. It's called logit. So rather than specifying family Bernoulli link logit, you can just type logit after it with a comma at the end of the model, and it will know that. So two different ways of specifying the syntax there. So family and link, or just specify logit. There are lots and lots and lots of these combinations you can use. So down the left-hand side, I've listed the families, the distribution families, and across the top, I've listed the link functions. So we have identity. The link functions are identity, log, logit, probit, and complementary log log, or C log log. And down the left-hand side, we have a bunch of different distribution families. Gaussian is normal, Bernoulli, beta, binomial. Notice at the bottom there are some of these that may be unfamiliar, like Weibel, gamma, log logistic, and log normal. Those are for an exponential. Those are for survival analysis. So you can actually fit survival analysis models as a component of a structural equation model. Now, in the table itself, what I've shown are the combinations that are allowed. D means that's the default. So if you don't specify or you use one of the nicknames, that's the default. And then X is an option. So for instance, Gaussian, for the Gaussian distribution family, the identity link function is the default, but you could use a log link function if you wanted to. Bernoulli, for the Bernoulli family, logit is the default, but you could use probit or you could use complementary log log. Same thing with beta, binomial, and ordinal. Logit is the default, but probit is an option, and so is C log log. Okay. So there are lots and lots of combinations of these, and it allows you to fit very, very sophisticated models that include continuous endogenous covariates and ordinal and multinomial and count and survival, all different kinds of endogenous variables in the same model. Okay. So let's look at some other GSIM examples here. Here I've included a multi-level latent variable. So multi-level latent variables have a double oval. It's like a double-walled oval here. So if I wanted to fit a model where I had kids nested within classrooms, I might want to include a classroom multi-level latent variable. Now, classroom has to be a variable in my model. In this case, the latent variable actually does have an observed variable in the data set because that's the ID, the grouping ID. Now, what's interesting about this is if you think about it when you look at the drawing, and I've drawn it this way intentionally, the outcome has an observation level error, level 1 error or residual, and then you can think of this second level latent variable as the level 2 variance or the level 2 error. It's going to estimate a variance for that level 2 latent variable. So we have the level 1 variance and the level 2 variance. Okay. Now, to specify that multi-level latent variable, we're going to have to write it in the syntax as a latent variable with a capital letter, M1, but then you also have to put square brackets and tell it the ID variable for the clusters. So again, I need a classroom variable in the data set that's my clustering variable. So Stata knows which observations go together in which cluster. Okay. And then again, you need to, it's good practice to specify the latent variable explicitly with that latent option. If you've capitalized the name of the latent variable, Stata will assume it's latent, but for your purposes and for Stata, it's not a bad idea to be explicit and put that latent option in there. Okay. So that would be a multi-level latent variable. Now, you can draw these models. You don't have to generate the syntax yourself if you don't want to. There is a structural equation modeling builder built into Stata. So you can open this and it has a toolbar down the left-hand side. And there are lots and lots of tools, and I'm not going to go through each one because it's just so many of them. But what I want to emphasize are the 4 main ones, which are going to be the top one here, this plain rectangle. That's an observed continuous variable. That's available in both the sim command and the gsim command. Okay, so that's an observed continuous variable. The second box here is, again, a box, but it has a header and a footer. The top is the distribution family, in this case, Gaussian. And the footer on it shows the link function. So we're going to use an identity link function. So that's an observed generalized response variable, and that's only available in gsim mode. I forgot to mention at the top left of the toolbar, there's a gsim button. So if you want to use some of these gsim features, you're going to have to click that gsim button. Because if you don't, some features are only allowed with gsim, and so that's how you can restrict that in the models. Okay, then the third item in the list here in the drawing is a single oval, and that's just a regular continuous latent variable. That's available in both sim and gsim modes, so you can use that single oval anywhere. At the bottom, we have this double oval, and that represents a multi-level latent variable, and that's available only in gsim mode. Okay. So those are the 4 objects that you're going to be drawing in your structural equation models or in your path diagrams. There are wizards. That's what some of these other objects in the toolbar do. They allow you to create measurement models quickly, and it aligns everything for you. And you can label things and put boxes around things. But it's really powerful, and you can export these in high resolution and just put the path diagrams right into your manuscripts or PowerPoint slides or whatever. It's how I generated all of these. So you can draw the model in the sim builder just like this. And when you're ready, you just click this little arrow. Look, it looks like a sheet of paper with a big right blue arrow on it. That's the estimate button. And that will open a dialog box that gives you your options for how you want to do the estimation. Okay. So sim builder. So any questions up to here before we look at some examples? Just the basic syntax and how you would set this up. Okay. Okay. So what I'm going to do is walk through some examples. And I had a class in structural equation modeling in grad school back in the 90s, but that was so long ago And the software was so different back then, and the way we approached it was so different that I kind of went back and had to teach myself all over again using Stata 20, 25 years later after I had a course in this. And the way I'm going to approach it is a little bit different. We're going to work some examples, but I want you to see how I'm going to build these up so you can see how different kinds of familiar models are special cases of structural equation models. We're going to be using this data set that I've put together. It's included in the download. It's called sim_data, and it includes the following variables. It actually has a lot of more variables. This is some of them. Student is the student ID. Classroom is the classroom ID. Age is the student's age measured in years. Male is an indicator for whether they're male or not. Math score is the overall math test score, and it ranges from 0 to 100. Math pass is an indicator for pass or failing a math test. So, and I think the cutoff was 70, like it often is. So 70 or above is a 1, 0 or below is a 0. Reading score is their reading score. And again, it ranges from 0 to 100. Read pass is, again, an indicator for whether or not they passed the reading test or not. EMO score is a standardized emotional depression score, and we'll come back and see how that's constructed shortly, but that's the emotional depression score, or EMO score. PHY score, I call it PHY score, that's the standardized physical depression score. And then drug score is also a standardized drug use score. So those are observed variables that I created in the data set so we can compare those with the latent variables that we'll see later on. Now, we also have the drug and alcohol screen variables in the data set. So I have an indicator for smoking, an indicator for alcohol, marijuana, opioids, and meth. And those are responses to the questions that you see in the variable labels. Do you smoke regularly? Do you use alcohol regularly? Do you use marijuana regularly? And so forth. Then we have the depression scale. So these are 10 depression questions. 5 of them are emotional depression questions, emotional depression symptom questions, like have little interest in doing things, feeling down and depressed. The last 5 depression questions, 6 through 10, are physical depression symptoms, such as loss of appetite or trouble sleeping, things like that. So these variables are also included in the data set. So those are the variables that we have to work with. So let's go through and look at some examples of structural equation models. So this is a path diagram for the mean of math score and the mean of read score. Now this looks absurd. What happened to all the covariances and the lines and the paths and all that stuff? Well, this is to prove a point that this is a path diagram for a kind of structural equation model. All I'm going to do is estimate the mean math score and the mean reading score. It is, however absurd, a path diagram. And I could do this using Stata's mean command. So at the top, I would just type mean math score read score. The equivalent sim command to do this would just be sim math score read score. Okay, I can use sim that way. I can just type sim math score read score. Now let's compare the output that we get. If I use the means command, I get the mean of each math score and reading score. I get the standard error and a confidence interval. If I do this with the sim command, I get a lot more information. So I get the mean of the reading score, the mean of the math score. So I get the mean, the standard error, a z-statistic, a p-value, a confidence interval. I also estimate the variance of the math score and the reading score and the standard error of the variance and a 95% confidence interval for the variance of those scores, as well as a covariance for the covariance between math score and reading score, and a standard error for the covariance and a z-test, a z-statistic and p-value testing that is different from 0. And I get a confidence interval for the covariance of math score and reading score. So as you can see, you get a lot more output from sim, and there may be times when you want to use this just to do things that seem a little off the beaten path. Like say somebody wanted to, for whatever reason, wanted to estimate, well, what is the covariance between math score and reading score, and what's the confidence interval for that covariance? Well, I can do that with sim. It shows up right here in the output at the bottom. Okay. So, but the point is, estimating means is a special case of a structural equation model. Rather than typing mean in the 2 variables, I just type sim in the 2 variables, and it'll estimate the mean along with a lot of other things. Correlation is a special case of structural equation model. So if I want to estimate the correlation between math score and reading score, now the path diagram are the two variables with the covariance curve drawn between them. Okay, that's all that is. So there are a couple of ways I could do this. One is with the correlate command. I could type correlate math score, read score. But with the sim command, I can type sim math score, read score, and then type comma standardize. What that's going to do is standardize the covariance. Standardized covariance is correlation. So if I look at the output at the top from correlate, all I get is a correlation matrix. So I one's on the main diagonal, and the correlation between reading score and math score is estimated to be 0.9463. Now that's fine. It gives me the correlation, but that's it. If I use the sim command, what that's going to give me is the output like I had before. It estimates the means, the standard errors, and so forth. But here's the interesting thing. It's labeled as covariance, but this is actually the correlation. It's the standardized covariance, which is the math, the correlation. So notice it's 0.946332, which rounded is the same as what we have in the correlation matrix above. But here's the cool thing about this. It also gives me the standard error of that correlation, a z-statistic testing whether that correlation is equal to 0 or not, and I get a 95% confidence interval for that correlation. Now, again, part of the reason this is good information to know and why you might want to do this someday is I worked on a paper with a friend years ago where they wanted to estimate correlations, but in whatever year it was, let's say it was 2015, you can't just report a correlation out of thin air. You need to include either a standard error or a confidence interval. So we reported confidence intervals for all of our correlations. Well, the only way you can get that is with Stata sim command. Okay. So if you want to estimate a correlation and put a confidence interval on it, sim is the command to do that. Okay. Now, linear regression is also a special case of a structural equation model. So I could draw a linear regression model with this path diagram. So let's say I'm interested in math score, and I think that age and being male are predictors of math score. Now notice age is continuous, male is a binary predictor, and so I can just include them. Math score is continuous. And I have my error term, or epsilon, hanging off the end over here on the left. I could do this with Stata's regress command. So I would type regress, math score, age, and male. Or I could use the sim command and type, the syntax is very similar, sim math score. Now I do need this little left arrow symbol, the less than and the dash, followed by age and male. So the syntax is very similar, but that little difference. And if I compare the output actually looks very similar as well. It's not going to be identical because they're two different computational engines, so you may see differences out in the third or fourth or fifth decimal place, but by and large, you're going to get the same results. Certainly in terms of the conclusions, like you're not going to see a p-value on one side of 0.05 from one and on the other side of 0.05 from the other. You're going to see differences out in the third or fourth decimal place. So the regress output shows us the coefficient, standard error, the t-statistic and p-value, and the confidence interval. We get the exact same thing from the sim command, but something else we get is the variance of the error terms. So it actually gives us an estimate of the variance and the standard error of the variance of the error terms, as well as a confidence interval for the variance of the error terms. And there may be times when you want to report that, and you can get that from sim. Regress doesn't give you that. It will give you an RMSE, the root mean squared error, but it's not going to give you the actual variance estimate directly. Okay. Logistic regression is a special kind of structural equation model as well. So let's say that math pass is a binary variable, binary outcome, 0 or 1, and maybe I think age and male predict that binary outcome. Well, I could do this with the logistic command, logistic math pass, age and male, or I could fit this model using the gsim command. So I would type gsim math pass as my binary outcome, and then I can type age and male after the arrow. And then at the end, I can either type family Bernoulli link logit, or I could just use that little alias. That's the word I was looking for before, alias logit. Just type logit there, or nickname. Now that is going to report coefficients. If you want to see odds ratios, the exponentiated coefficients, you would type estat form. And if we look at the output from these, the logistic output at the top shows us the odds ratios for age male and the intercept _cons. If we run gsim followed by estat eform, we get a output that looks pretty much the same. Okay. So logistic regression is a special case of a generalized structural equation model. Now, what about multi-level models? So here, let's say that we have math score, but the kids in the class, the kids are nested within classrooms. And I'd like to take that into account, that nesting. So I'm going to do that with a multi-level latent variable here, this double oval that says classroom. So I could do that with Stata's mixed command. So the mixed command, the dependent variable is math score, and the independent variables are age and male. And then I would put 2 vertical bars followed by the nesting variable classroom, followed by a colon. So that's how I would fit a model like this using the mixed command. Using gsim, the equivalent command is to type gsim math score, followed by the arrow male and age. But rather than putting 2 vertical bars, I'm going to specify the nesting using a multi-level latent variable. So this M1 is going to be the multi-level latent variable, and I'm going to include the classroom variable in brackets, square brackets. So that's the equivalent syntax for mixed and gsim. And if I look at the output looks almost identical as well. So at the top, I get estimates of the fixed part of the model, the age, male, and underscore cons coefficients. And below that, I have my random effects, the variance of the level 1 or observation or residual level variance, and the classroom level variance. And the GSIM output, I get the same stuff. I get the coefficients for the fixed part of the model and estimates of the variance, the observation or residual level variance, and the classroom level variance. And notice that they're virtually identical out to 4 or 5 decimal places. Okay. So again, multi-level or mixed effects models are a special kind of generalized structural equation model, and that's how you would translate the syntax from one to the other to GSIM. Multivariate regression is also a special case of a structural equation model. So this is what the path diagram would look like. So let's say we want to fit a model where we have 2 dependent variables, both math score and read score are dependent variables or endogenous variables in this context, and age and male are going to be our exogenous variables or predictors of both math score and read score. And we're going to assume that the errors for these are correlated because they come from the same kids, and math scores and reading scores are, at least it's safe to assume they're probably correlated. So we're going to allow correlation between those error terms. I could do this with Stata's mvreg command. So the syntax would be mvreg followed by the 2 dependent variables, math score and read score, equals, I need an equal to know where the split is between independent and dependent variables, and then age and male. There are 2 different ways I could do this with the sim command. I could type sim and then put math score, read score on the left side of the arrow and age and male on the right side. So endogenous variables on the left, exogenous variables on the right. And then I need to explicitly specify the covariance between those errors using this COV option. Okay, and the E dot says it's not the covariance between math score and read score, it's the covariance between the errors for math score and the errors for read score. Now that's one version of the syntax, and depending on your preferences or the area you work in, that might be your preferred way of specifying this. I have a tendency to write, I think I spend too much time around economists. I tend to think of this as a simultaneous equation model. So you could write this as sim and then type math score and have the arrow and age and male on the right, and then have in a separate set of parentheses, put read score and the arrows and age and male. Okay. Now, this also emphasizes the fact that you can have different exogenous variables or different predictors for math score and read score if you wanted to. In this case, I'm not, but if you wanted to, you could have different sets of predictors for each of those scores. And then again, we have the covariance between the error terms in the bottom. Either one of those forms of syntax will work. I don't think syntaxes is a word. So this is the mvreg output, and I can't get all the output in one slide. It's just becoming too much to fit it in one slide and be able to read it. But I get coefficients for the predictors in each of the outcomes, math score and read score. Or I can look at the sim output. Now notice sim, I get those same coefficients that I got from mvreg and in the same basic format, but I also get a estimate of the variance of the error terms for the math score model and the read score model. And I get an estimate of the covariance between those error terms. So I get a lot more information using sim than I do from using MVReg. But again, they are equivalent ways of writing the same kind of model. These sim models at the bottom are essentially just multivariate regression models using the sim command. Okay, now let's make a leap off into something that's a little different. These are often called measurement models in the psychometrics world. So we're interested in the combination of a collection of variables. So in this case, I'm going to look at depression questions 1 through 5. Now, in the old days, this is not how we do this anymore, but in the old days, I'm old enough to remember actually doing this. We would take these 5 questions and we would add them up. So what I've done here is use the egen command to create a row total of those 5 questions. So what I'm going to do is add them up and form a variable called sum emotional. That's the sum of the emotional variable outcomes. And then I'm going to standardize it. I'm going to subtract off the mean and divide by the standard deviation, which converts it to a z-score. So the next command at the bottom that says egen std emotional, what I'm going to do is I'm going to use the std function for standardize. I'm going to standardize the sum of the emotional scores. What that's going to do is convert these 5 questions into a z-score, basically. So that's what that's doing. If I were to plot that final variable, this standardized emotional depression score, notice that it kind of has a hump shape to it, centered around 0 because it's been standardized. And so the horizontal axis here is standard deviations away. So there's about a 4 standard deviation range, a little more than 4 standard deviation range of emotional depression scores. So that is an old-fashioned way of creating an emotional depression score. And we could take that emotional depression score and we could use it as a predictor in a regression model. So maybe I take that standardized z-score for emotional depression questions and use it as a predictor of math scores. And then I can use Stata's margins command and margins plot to look at the relationship between the standardized emotional depression scale. Again, notice it's on a z axis, a z scale here at the bottom. And the vertical axis here is expected math test score. So no surprise, the higher your emotional depression, the higher you are on the emotional depression scale, the lower your expected math score. Okay, no surprise there. Now, this is an old-fashioned way of doing it. The modern way of doing this is to use a latent variable. Now, the latent variable isn't doing exactly what I just did, but by analogy, it's kind of like what it's going to do. It's going to create a continuous variable for emotional depression. And we're giving it the label emotional depression. Notice we're imposing that idea on these 5 questions because we just read the labels. Have little interest in doing things. Have down, depressed, or hopeless feelings. Feeling bad about yourself. Thought you would be better off dead. Trouble concentrating on things. If we read all of those, we kind of think, well, those sound like emotional depression symptoms, and that's why I've given it this name. I could have given it a different name. The point is I'm making up this name. I'm putting that label on this latent variable. So it's not a thing. It's a construct or a concept that I've imposed on these 5 questions to label it. And then under the hood, Stata is going to estimate a continuous latent variable for that. Now, these questions, for now, we're treating them as the way I've drawn them with the plain boxes. These are treated as continuous outcomes. Depress Q1, depress Q2. I'm treating those as continuous outcomes. But if I look at each of the responses to each of these questions, they're actually Likert scales. They're ordinal. So the responses are strongly disagree, disagree, neutral, agree, and strongly agree. So again, 20, 30 years ago, you could have gotten away with treating these as continuous and done it like I just showed you, adding them up and standardizing them. But in 2025, you're not going to get away with that anymore because we have more modern tools to deal with these or model these kinds of variables as they are. Depression questions 1 through 5 have ordinal responses, and we need to treat them as ordinal in our model. Now, the nice thing is that GSIM will do this. So I'm going to specify an ordinal distribution, or that we're going to treat them as ordinal variables, and I'm going to use the logit link function. So essentially, we're going to be fitting an ordinal logistic regression model for the relationship between emotional depression and depression questions 1, 2, 3, 4, and 5. Okay. So this would be the more technically correct way to do this, is treating the outcomes as ordinal. Now, the nice thing is that we can do that very easily, and depression questions 6 through 10 are similar. They're also measured on a Likert scale. And again, reading through the questions, I'm imposing the idea that these are physical depression symptoms. And I believe that emotional depression and physical depression are probably correlated with each other. If you have physical depression symptoms, chances are you also have emotional depression symptoms. So we're going to allow those two to correlate. And this also emphasizes the idea that latent variables can covary, just like observed variables. Latent variables can also be correlated with each other. Now, the drug use measurement model. Remember, I mentioned earlier on that it's a good idea to fit these separately. So I'm actually fitting these models separately and making sure I'm modeling them correctly. And if I were doing this in real life, I would look at the fit statistics for each of these models, each of these submodels or path measurement models independently, separately. So now I'm going to create a measurement model for drug use. And I have these 5 indicators for smoking, alcohol, marijuana, opioids, and meth. Now, these are binary variables, so treating them as continuous is really absurd here. We're not going to do that. Each of these is an indicator, yes or no. And so what I'm going to do here is specify a Bernoulli family, distribution family, and a logit link function. So we're talking about a logistic relationship between the drug use latent variable and each of the outcomes, the binary outcomes. So again, we're using GSIM to model these the way the data actually is, not treating them as though they're continuous or pretending that they're continuous. So now that I have these 3 latent variables, I might start thinking about the relationship among these latent variables. So now I'm not so much worried anymore about the individual questions. I want to start thinking about those latent variables as the actual thing that I'm interested in. I'm interested in the relationship between emotional depression, physical depression, and drug use. So I could allow these to covary, but what I might start thinking about here, and I'm only speculating, I'm not a psychometrician, I'm just kind of speculating. I'm thinking, well, emotional depression might influence physical depression. Chances are you're emotionally depressed first, and that could lead to physical depression symptoms. I feel sad and all these things, and so I don't sleep well, or I lose my appetite, things like that. So I think emotional depression could influence physical depression, and emotional depression could influence drug use. I don't feel well, and so I smoke more, or drink more, or do whatever. So rather than, again, specifying covariance between these, I want to actually measure is there a relationship between emotional depression symptoms and drug use. Drug use itself could also lead to physical depression symptoms. I can't think of a good example, but maybe one of these leads you to not sleep very well. And so that's a way that I could draw the relationship between these 3 latent variables. And again, as I mentioned earlier, when we were talking about the question of how do you build these, I'm sort of building this up piece by piece. I looked at each of the components first. I want to make sure that they fit the data correctly. And now I'm going to start thinking about a more sophisticated model. And this also emphasizes that latent variables can be exogenous or endogenous. They don't have to always be exogenous. Now, what I may do is I may start thinking about the relationship of all of these things to math scores. Maybe the thing that I'm ultimately interested in are what are the predictors of math scores. So maybe I think emotional depression influences math score, drug use influences math score, and physical depression could influence math score. These students who take these tests are nested within classrooms. So I'd like to account for that fact by using a multi-level latent variable. So this whole thing is going to be a gigantic multi-level model. So I'll have observation level residuals and classroom level residuals. And I'd like to take into account whether the students are male and what their age is. So that's how I've worked my way up to this very sophisticated structural equation model. Now, to fit the model, this is the syntax. If I were to draw this or write this path diagram as in the syntax, I would argue that this is the simplest form of the syntax. So I have emotional depression predicting that latent variable predicting depression questions 1 through 5. Physical is questions 1 through 6 through 10, and so forth. I'm not going to read it all to you, but that's a nice clean version of the syntax. Then at the bottom, I'm going to use Stata's predict command to predict the latent variables. And you can do that. You can predict what are the estimated values of the latent variable drug use. What are the predicted values of the latent variable for emotional? What are the predicted values for the latent variable for physical depression and so forth? You can also get standard errors for those. So when I fit the model, these are the path coefficients that are shown along each of the arrows. So I can see and notice that there's always one that's 1. You need sort of an anchor path that's constrained to be 1 so that you can estimate the others. It's like having a categorical predictor in a regression model. You have to pick one of them as the referent category, and that's essentially what we're doing here. So anyway, we can look at these. The ones for the individual measurement components aren't as interesting unless you just compare the magnitudes of them, which question tends to influence the latent variable more. But what I'm more interested in are what are the relationships between the latent variables and math score. So emotional depression, remember these can be thought of as sort of like a z-score, standardized score. And so emotional, each unit or each standard deviation of emotional depression decreases your math score by about 3.3 points. That's what that minus 3.3 means. Drug use, now clearly these are simulated data, and clearly I messed this up because this is saying that each one standard deviation increase in drug use score is associated with a 9.7 point higher math score, which clearly that doesn't make sense. But anyway, that's my fault. When I simulated the data, I got that backwards. And then the physical depression symptoms. Physical depression, each standard deviation higher physical depression score is associated with a 3.7 point decrease in your math score. Similarly, being male lowers your math score by 3.1 points. Each additional year of age increases your math test score by about 2.2 points. So again, that's how we would interpret those path coefficients, is in a similar way to regression coefficients. Now, we could also plot these. Remember, we predicted the latent variable scores. So if I look at the horizontal axis here, the horizontal axis is the predicted latent overall drug use score. So again, think of this as a standardized drug score. So these numbers represent z-scores, sort of. So higher scores mean more drug use. So the higher your overall drug use score, what I have on the vertical axis then is the predicted probability of using a particular drug. So the higher your overall drug use score, if we look at this orange line on the top, that's the probability of smoking. There's a clear relationship there. The higher your drug score, the higher your probability of smoking. This is a similar relationship, though not as exaggerated, for alcohol use. Marijuana, the blue line, that's also has somewhat of a higher probability as your overall score goes up. Notice at the bottom, it could just be the scale, but meth, that doesn't seem to be affected much by your overall drug use score. And there's a low probability of that, of meth use, no matter what. Opioids shows a slight increase as the overall drug use score goes up. So anyway, the point here is that I can examine the results of this is just the drug use measurement component. And I can look at the relationship between the latent variable and each of the individual observed variables, alcohol, smoking, marijuana, and so forth. I also might want to look at the relationship between predicted latent emotional depression. Again, these are on a z-score, z-axis on the horizontal axis, and the predicted or expected math scores. So no surprise here, the higher your emotional depression score, the lower your expected math score. And so I've shown a scatter plot of that here. And this looks like a pretty linear relationship. So coming back to, does the model accurately reflect the underlying data or patterns in the data? This suggests that it fits in pretty well. It is a linear relationship. Same thing with physical depression. So this is the predicted latent physical depression. Again, the higher your latent physical depression score, the lower your predicted math score. And that is a fairly linear relationship there. Okay. And so that is a version of the model and some predictions and interpretations we could get out. Now, we might want to elaborate on this. We might want, before the last model we fit, we didn't allow for relationships between the latent variables. We could go back and add those in and take the other things into account. I didn't put the results in here, but we could examine different models to see which models fit the data best. Which then raises the question, how do we assess whether the model fits the data well or not? Well, as I mentioned earlier, this is a huge closet industry of how do you measure model fit? And this is only a partial list. There are many more of these. These are the sort of popular ones, and these are all included in Stata. So there's the likelihood ratio chi-square test. The ones at the bottom, you see these a lot, these CFI and TLI, comparative fit index, the Tucker-Lewis index, lots of these in here. As I mentioned earlier, one of the unfortunate things about these is that they don't always agree with each other. So you may have 3 or 4 of them that say, yeah, the model fits pretty well, whereas 1 or 2 of the others may say, no, it doesn't fit very well. So that then raises the question, well, which one should I use? If they disagree, then which one do I use? The only advice I have is pragmatic. I would not go shopping for these and then only report the ones that agree with what you want to say. That's not really fair and not good ethical practice. But I would suggest being pragmatic about it. I would look at the other papers in the journal that you are submitting your paper to and see which fit statistics they use. Typically, certain journals, the editors of those journals will typically request certain fit statistics. Some really prefer CFI, some really prefer TLI, or some may want RMSEA and TLI for whatever reason. But go to the journal where you're going to submit your paper, look and see what is typically reported, because that's probably what they're going to ask for, and make sure you do those and report those. But again, don't go dredging your data for fit statistics that show that yours fits well. Okay, so last but not least are other resources. The Stata manual is an extraordinarily, and I had nothing to do with it. I know I work for Stata, but I had nothing to do with the writing of this manual. So I don't feel bad saying that this is an extremely well-written manual, the SIM manual. So that's a really good resource, and it shows lots of different kinds of models along with their path diagrams and syntax. And it's freely available whether or not you have Stata. I put a link to it here at the bottom. So even if you don't have a copy of Stata, this is the 17 manual, but go check that out. We also publish a book through Stata Press by Alan Aycock called Discovering Structural Equation Modeling Using Stata. And again, it's about structural equation modeling specific to Stata. And there's a revised version of that one out. So you might check that out. That one you will have to pay for. It's available through the Stata bookstore and you can order it there. Now, 2 other special cases. One is a book. In fact, I was the technical editor for both of these books, and they're both excellent. One on the left is by Scott Baldwin called Psychological Statistics and Psychometrics Using Stata. It's not explicitly about structural equation modeling. It's about psychometrics, and it has a lot of other topics such as ANOVA and regression, and exploratory factor analysis and things like that. But it does include a lot of things using structural equation modeling in the book, as well as a kind of a brief introduction, as well as advanced use of structural equation models. So I can't recommend this book highly enough. If you're doing anything in psychometrics and you're using Stata, I strongly recommend getting a copy of this book. It's really, really well written, covers a lot of important topics. On the right is another book that I was technical editor for called A Course in Item Response Theory and Modeling Using Stata. This is written by 2 major experts in the field. One is Tinko Rykov. He actually has a statistic named after him. And then George Markolides, who is one of the founding editors of the journal Structural Equation Modeling. And I believe he's still editor of the journal Structural Equation Modeling. Anyway, these are 2 very famous heavy hitters in the world of structural equation modeling. Item response theory is a special kind of structural equation model, and they use SEM in the book. So again, you might check that out if you're going to be doing any item response theory. Now, this may seem a little weird, but they actually include structural equation models in these. In the latest edition of, this is the, what, fourth edition now of Sophia Rab-Hesketh and Anders Skrondel's books on multi-level and longitudinal modeling using Stata. There are two volumes. Volume 1 is continuous responses. Volume 2 is categorical count and survival models. I mentioned earlier that GSIM allows you to fit those kinds of models and in a multi-level context. And so they include examples of those in these books. So even though they're not explicitly about structural equation modeling, they do use examples from structural equation modeling in the context of multi-level and longitudinal modeling. Okay. So again, you can download all the materials at tinyurl.com/2021sim. That includes all the slides, data sets, do files, as well as I saved the files for the path diagram. So you can just open them and look at them and see what they look like, and then play with the drawings if you like there. So thanks for being here. I'm not in any hurry, so I'm happy to hang out and answer questions as long as you like, until one of us gets hungry enough to say we've got to go away. And then if you think of questions later on, just shoot me an email at chuber@stata.com. So thanks again for being here. Thanks, Joni, for setting all this up. And thanks, Margaret, for all your hard work setting this up as well.
Well, thank you, Chuck. This was amazing as always, and I see most of our group
thank you.
here, core group stayed because your presentation was so engaging. So thank you.
Well, thank you.
Does anyone have any questions they'd like to pick Chuck's brain about before they hop off? Oh, Conrad, go ahead.
Yeah, thank you. I was just wondering in your, I guess your sample size of the 5 to 20 observations rule of thumb, is there a better way to determine where in that range you will be before you embark on something that might not work?
Okay, that's an excellent question, and I actually need to put a slide in here to address that, but I don't have it. If you go to your favorite search engine and search Stata blog, sim, and power or something like that, but make sure you include Stata blog, power, and SEM, it will take you to a blog post. I don't know how long ago it's been now, maybe 8 or 9 years, 7, 8, 9 years ago. I wrote a whole series of blog posts on how to do power by simulation. And it starts off with how to do power by simulation for a t-test, because that's simple enough that you can check your work with Stata's regular power calculators. And then there's a whole series of them, about 4 or 5, and it ramps up through how to do power by simulation for linear regression and logistic regression and then multi-level models. I got stuck on the last one for sim, and we hired a lady, I guess about 5 or 6 years ago now, named Megan Kane, who's actually a psychometrician. I just pretend to be. I'm actually a biostatistician who dabbles in sim, but she's a card-carrying psychometrician from Notre Dame. And one day I happened to mention that, yeah, there was a blog post I started on sim, and I never finished it because I got stuck on some things. And she's like, "Oh, well, do you care if I finish it?" So I was like, "No, have at it." I gave her what I had, and she got unstuck. She knows enough about that stuff to get unstuck and then finished it up. There's a long-winded way of saying there is a nice blog post that Megan wrote on the Stata blog about how to do sample size calculation or power calculations for sim models using simulation. And it's really, really clever. And that's a much better approach than just saying, oh, well, 5 to 20 per, blah, 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 blah. You could actually do power by simulation and get a pretty good idea of what your power would look like. So, yeah. And to my knowledge, that's the only place where you can go see an actual worked example of how to do it. Books will always tell you that, and that's very frustrating to me, and it's why I wrote the blog series. Is textbooks will say, well, at this point, you're probably gonna have to do power by simulation. And then that's it. They don't show you how to do it. They just tell you that you should do it, sort of pretending like everybody knows how to do power by simulation. So as far as I know, that's the only example I've seen, and she wrote it, of how to do power for sim models by simulation. So yeah.
I think you're right. I'll dig it up. When I worked at UCLA, we found a web page that basically is a simulator for power analysis in sim, and it's based on a paper. And it will simulate it for, I know they'll do it for like single mediators, parallel mediators, and there's a couple of different options it'll do it for.
Yeah.
And it requires you either to know the correlations amongst your variables or the means and standard deviations for them. I will dig that up in a minute and I'll put it in the chat for people if they're interested.
Yeah.
Mhm.
The ability to do power calculations by simulation is a gold mine. Once you get good at that, you can crank your consulting rates way up because it turns out there aren't many people who know how to do that. I always thought it was just something people did, but it turns out it's not. It is a very unique skill, and it's not that hard if you spend a little time on it. So, speaking of UCLA, quick shameless plug. It's not me per se, but I'm writing it. I am in the process of writing a companion webpage to the Stata YouTube channel. So one of the complaints has long been about the YouTube channel. Well, you can see it, but then the code isn't there. We can't just copy and paste the code and use it. So I'm writing a companion page for each of the YouTube videos that actually shows how to do stuff, and it'll have all of not just the code, but like a written explanation of things. It's a bit more like the UCLA webpage. So I've only started on it. I started on it last summer and worked on it some over the holidays when I was home. And I'm hoping this summer to get back on that. So if you have suggestions of things that you would like to see on that, certain topics that you're like, oh, it'd be nice if there was a web page that showed how to do this, send me an email, same email, chuber@stata.com, and I'll see if I can put that in this summer. Any other questions? Okay. Well, I guess we will wrap it up there.
I put for those who are interested, I put the link to the UCLA page and to the online application that does a Monte Carlo simulation for sample sizes for simple mediation, parallel mediation, and then serial mediators. So that might be of interest to people.
That's
Okay.
super helpful. Thanks, Joni.
You are quite welcome. All right, well, no other questions, going once, going twice, sold. All right.
We're done.
We will
Thank you, Chuck.
yeah, thank you as
Thanks.
always. And